Hey guys, Mr. Smith here, and we're doing our last lesson in Unit 5. We're going to be making some connections with trig functions. Today, part of what we're doing today is we're going to be modeling real-life situations that are periodic but might not involve angles. And the little introductory paragraph here mentions a few: speed wobbles and motorcycles and bikes and aircraft where you have that just periodic wobble back and forth. Even though that's not necessarily angle related, you can model it with a periodic function. A mass on a spring bobbing up and down, you can model with a periodic function. A pendulum just swinging back and forth, you can model with a periodic function. So many things. We're going to make some connections with that. What I want to start off doing, though, we're going to start off by looking at the sine function and rates of change with the sine function. When is it increasing? When is it decreasing? When is the rate of change in the sine function the highest? And what is that highest value? So things like that. So I've included in our lesson folder for this lesson, I've included a link to this Desmos kind of investigation. So if you guys open up that link, the QR code's there. You can bring it up on your phone. You should get something that looks like this. And I have that brought up right here. So I have that loaded up. So what I have is I've graphed the basic sine function in red, and I've made a slider that plots points on the sine function. And so as you can see, as I change the slider, it just gives me the point on the sine function for whichever value of a the slider's at. So if I want to, if a is -4, I get the point -4 about 0.7057. And you can play around with that. The second thing I have here is I have the Desmos set to give me the tangent line for the sine function at these curves. So when I click it on, you can see it draws it in. Why and the how of why this works, that's something for calculus. So don't really worry too much about how I did that. But there's a tangent line for you. And as you can see, as you drag the slider back and forth, it updates the tangent line too. And I have some guiding questions for you guys. Once I kind of go through these, please take some time and do them, and then we're going to talk through them together. Well, I'll talk through them and you'll be at wherever you're at. But yeah, please play around with it and then think about the following. So on the interval from 0 to 2 pi, when is the instantaneous rate of change positive? When is it negative? And I want you guys to see if you can find out when the instantaneous rate of change is the absolute highest it ever gets. And what is that highest rate of change? So for example, so right now you can see the instantaneous rate of change at 1.1, x equals 1.15. You can get by estimating the slope of this line. And you can see as I get closer to the maximum, that rate of change is lower, a bit lower, a bit lower. In fact, when you get to the maximum, it would be 0. But you can see as I get closer and closer, as I move down the curve, my rate of change is increasing. The slope of this tangent line is increasing. So I'm asking you guys, play around the slider. At what x value do you get a tangent line that has the biggest slope possible? So yeah, pause the video, guys. Give that a try. Also, you want to find when you get the lowest rate of change. And so pause the video and unpause when you're ready. So, my battery's running low. Let me pause my video and plug that in. All right, and we're back. Computer's not going to die on me. So let's take this up. When does the instantaneous rate of change appear to be 0? I kind of teased this a little bit, but the instantaneous rate of change, the slope of this tangent line, is 0 whenever you reach these maximums and minimums. When is it increasing? When is it decreasing? So on 0 to 2 pi, when is it increasing? So 0 to 2 pi is like 0 to about 6.28. So you can see it's increasing from 0 up until where sine usually hits its max, which is pi over 2. It then decreases, because the slopes of the tangents are negative, the function is decreasing from pi over 2 to 3 pi over 2 down here. And then the graph is increasing again up to 2 pi. So let's get those down, just quickly summarize that. So this is true whenever y equals sine x has a max or min. When is the instantaneous rate of change positive? So when x was between 0 and pi over 2, or x was between 3 pi over 2 and 2 pi. When was it negative? Between pi over 2 and 3 pi over 2. All right, here's the cool thing. So what value gave you the largest rate of change, and what is that rate of change? So if we go back here, so I'm going to go back between 0 and 2 pi. Okay, so here we have the positive rates of change, and it's the slope of this tangent line is getting steeper and steeper and steeper. And at some point, it gets as steep as it gets, and then starts getting shallower and shallower. And what point corresponds to the steepest it gets? 0, 0. And if you look at the slope of that tangent line, look at the rise. 1 unit, the run. 1 unit. Up 1, over 1, up 1, over 1. The slope of that tangent line is 1. So if we go back here, the value of x that gives the largest rate of change, x equals 0. And this gives an instantaneous rate of change of 1. That's as high as it gets. So that's pretty neat. Now there is some symmetry with the sine function. So if you figured that out, it's not too much of a stretch to reason out that the minimum is going to be at this point here. Won't give me exactly pi, but we can get pretty close. When x equals pi, and the slope of the tangent line, if we could do this perfectly, would be, and due to the symmetry, you can kind of see, it would be negative 1 and not positive 1, but the same steepness as the other guy. So that's pretty neat. X equals pi, and the instantaneous rate of change equals negative 1. All right, so some pretty cool things about the rates of change in the sine function. When you guys take your calculus course, you're going to make some further connections and dig a little bit deeper with that. That should be pretty fun. And a little bit of a teaser, you'll learn why in the equation of my tangent line, why cosine pops up. That's for calculus. We gotta lay the foundation first. All right. So we're gonna do a few odds and ends today. One thing we're gonna do is we're gonna look at some rates of change in more detail. So here we have a Ferris wheel, and we have the height of this Ferris wheel as you surf around the Ferris wheel after a certain time, and we're gonna determine the average rate of change for some smaller and smaller and smaller intervals. And this is going to give us an idea of the instantaneous rate of change at 10 seconds. And then we'll just talk about, a little bit of an interpretation about what that tells us. So we're going to do the first calculation purely by hand and then rely on Desmos to help us out a little bit for the second one. So from 5 to 10 seconds. So to find the rate of change, we're going to find the height at 10 seconds, subtract the height at 5 seconds, divided by 10 minus 5. So what would that look like? So we would have the average rate of change over this time interval. It's going to be height at 10 seconds. So 20 times the sine of pi times 10 over 60 plus 25 minus 20 times the sine of pi times 5 divided by 60. And we should put that in brackets, plus 25, all divided by 10 minus 5. So guys, I'm going to suffer along with you here. I'm going to whip up my calculator, and we're going to try this one together. And then we're going to bring up Desmos, and I'll show you guys how we can get Desmos to do this one for us. All right, here we go. So I'm gonna make use of brackets in my calculator. I'm also gonna make sure that I'm in radians, so I don't want to waste a bunch of work. So 20 times the sine. And here's a little tip, actually, just to make this a bit faster, because we're gonna have plus 25 and we're subtracting 25. So the 25s won't even factor in. So that's gonna save us a bit of time. A little tip for you. Sine of, so that would be 10 pi divided by 60 minus 20 times the sine of 5 pi divided by 60. So on the top, I'll keep a bit of accuracy. I got 4.8, I guess I'm using pink now, 4.8236, all divided by 5. And when I divide that, I get about 0.965 for our average rate of change. So, and if we think about what H is in meters, and T is in seconds. So this is in meters per second. And we'll talk about the significance of that rate of change, or the units anyway, in a little bit. All right, so let's make use of Desmos for the next one. So what we're going to be doing is we're going to be finding the height at 10 seconds minus the height at 9 seconds, and then dividing that by 10 minus 9. So we know this is going to be 1 on the bottom. But what's h at 10? What's h at 9? So let's get Desmos out here. Let's get Desmos to do some work for us. All right, so I just got a blank Desmos loaded up here, and we're going to create a function. I'm going to call it f of x equals, and I'm going to type in our function here. So 20 times the sine of pi times t divided by 60, close bracket, and then plus 25. And I'm going to add a table. I said x when I wrote t, so I'll make that x. Actually, I think I'm going to just call an audible here, and let's just use the same variables. It should be fine. H of t. Okay. And then we're going to add a table of values, and we're going to make these, call that t1, and then we'll make this h at t1. And then for different values of t, it's going to give us different values for the height. And we want the heights at 9 and 10. Let's punch them in, and there we go. And now we just got to copy them over to our page. So the height at 10 was 35. The height at 9 was 34 point something. It's 34.07981. And let's just round that to 3 decimal places once you do that subtraction. 981. So about 0.920. Okay, so now that we've got Desmos ready together, I'm going to pause my recording and do the final 2, and then you guys do the final 2 as well, and then unpause when you're ready. All right, guys, so I got the heights at 9.9 and 9.99 meters, and I use the average rate of change formula in this case, and I got 0.908 and then 0.907. So seems pretty reasonable that the value of the instantaneous rate of change at 10 seconds, and remember, one of our strategies for estimating instantaneous rate of change was to find the average rate of change for 2 points very close together at that desired point of tangency. It looks like our values here are pointing, or approaching 0.907 meters per second, getting very close to that. Let's just chat about C. What physical quantity does this instantaneous rate of change represent? So remember, our function h of t is describing the height of the car over time. And so this instantaneous rate of change is giving, it's in meters per second, it's a speed. Here, the instantaneous represents the vertical speed of the car at t equals 10 seconds. Not the actual speed, because our height, our function is only measuring the height above the ground. So this is measuring that vertical speed of the car. And then for D, would we expect the instantaneous rate of change to be the same at 15 seconds? So maybe you just want to have a quick think about that and pause the video. But, this is a sine function. Our sine functions go up and go down. And just like, even as I'm like drawing the tangent line, and you can think of the instantaneous rate of change, as you move along and go to different values, you can see the rate of change is constantly changing. It's going from increasing to decreasing to vice versa, hitting zero in between. So it's not reasonable to assume the height at 15 would be the same, because the sine function is continuously changing its slope. I'll just say the IROC at t equals 15 seconds is not expected to be the same. I mean, it could be like just by coincidence. And the reason this is because the sine function, its slope is changing continuously. All right, so tying in some stuff we already knew about instantaneous and average rate of change, tying it into a sine function. And we looked at, for the basic sine function, where that rate of change was highest and lowest, and it occurred at 0 and pi. And what was really cool is that the biggest rate of change was 1, and the smallest rate of change was -1. That has some huge impacts for next year when you guys take calculus. All right, the next thing we're going to do is we're going to model. So what we've done so far is we've done a lot of, hey, here's an equation, make a graph, or here's a description, or maybe even here's a graph. Can you make an equation by reading off the amplitude, the period, and the axis? But here we just have some data. And we're going to take this data and create a model, an equation for this data. We're going to do it kind of by hand, like we've done in the past. And then we're going to go to Desmos and actually make a regression curve. We're going to fit a sinusoidal curve to this data and see how our model did with the actual computer best model. All right, so let's start by determining the amplitude. So we normally get this by looking at the maximum value and looking at the minimum value. Now, we don't ultimately know what the exact max and min were. We only have these temperatures for the month. We can take the max and the min and average them out. So with the amplitude, we're going to take the highest, which is 22.4, and the lowest, which is -14. And divide by 2. I'm going to get into trouble here doing mental math. 36.4 divided by 2. And so our amplitude, 18.2. Let's do the axis as well, because we find it in a similar way. The axis is halfway between the max and min. So 22.4 plus -14 divided by 2. That would be 8.4 divided by 2. So 4.2. All right. What's the period? Well, I mean, it's the variations in temperature for the whole year. So we're expecting the period to be 12 months. It's the average temperature for a year. And so let's find K. So the way we usually get K, we do 2 pi divided by the period, which in this case is 12. So our value for K, we can leave in exact terms as pi over 6. All right. The last thing is D. So um, let's have a little think on this. So remember the sine function, where does it have its first maximum? A quarter of the way through the period. So I'll make a little blurb on this. Normally, sine function has a max 1/4 of the way through the period. And in this case, that would be at t equals 3. However, is that where our maximum is? No, our maximum looks to occur when t equals 7. T equals 7. All right, so what kind of shift is this? Normally, the maximum would be at 3, but ours is shifted to 7. So it's shifted to the right by 4 units. So our phase shift is going to be 4, in this case, months to the right. So to get our value for D, we do what our max actually is, minus where it originally should be without a phase shift, and we get 4 months. So you can always reason out the phase shifts. You can do the same thing with minimums or the first 0, but it's usually easier to pick a maximum. So our max occurs when t equals 7, normally a sine function that occurs at a quarter of the way through the period, which would be 3 in our case, and that corresponds to a phase shift of 4 months. And we got everything we need. So our function might look like this: 18.2 times the sine, big brackets, of pi over 6 times m minus 4 plus 4.2. So pretty neat. We've taken some data. We've made our own regression curve. So we're going to, so we've done part A. We're going to now head to Desmos, and we're going to make a scatter plot for this data, and we're going to graph our axis or our model and see how we did. And then we're going to see what the computer actually gives us for a curve of best fit. And I think we'll see we did pretty well. All right, so I have Desmos loaded up here with my graph pre-drawn. So if you want to pause and get this up there. So I added a table of values in this x1, y1. I made my table of values, and I changed my axes. I made my x to go from -2 to 15 to display everything, and I made my y values go from -20 to 30 to display everything. And very important that we're working in degrees here. So if you want to pause and have yours match up with mine, then we're all working on the same thing. But yeah, let's graph the equation of the curve we found and see how we did. This is kind of exciting. So y equals, so we had 18.2 times the sine. So it was pi divided by 6 times x minus 4. So instead of t and m, we're just using y and x. And then our axis was 4.2. All right. So you know what, guys? I'll shift myself up here. All in all, like not too bad. It fits pretty well at some parts, and then at others a little bit off, but not too bad for some human beings. Um, let's see what Desmos produces for a curve of best fit. So the way you perform a regression in Desmos, it looks like this. So I'm going to be using the data entered in table 1 with x1 and y1. And the way we do that is this. We do y1, and then to make a regression curve, we use this little tilde here. So that's usually that's beside the 1 on your keyboard. And now we'll type in our function. So uh, um, in a general sense, so we're making a function of the form a times the sine of k x minus d plus c. So we can type in a times the sine bracket k times x, and this is important. You want to do x1, so it takes the values from your table. X1 minus d, close a bracket, plus c. So this is really neat. So what Desmos does is, and what any program would do, it uses an algorithm that you guys might learn about if you take data management or if you take some statistics in university. But it finds the values of A, K, D, and C that fit the data as closely as possible. And so they have A being 18.27. We did pretty good there. K is 0.5, and pi divided by 6 is about 0.52. So we did pretty good. D is 4.1. We had 4.2. And D was 4.1. We had 4. And C was 4. They have 4.05 and we had 4.2. So we're actually, we did pretty good. So here's ours and then here's theirs. Theirs fits arguably a bit more nicely. Hey, guys, but I'd say we did pretty good. My expectations of you guys, given some data, would be to perform a regression like so, like we've done here. Show me how you get A using the max and min as well as C. Show me how you get K, and then show me that reasoning about how you get the phase shifts by looking at the maximums. So that's pretty fun, pretty good one. So the regression equation, just to get this into our notes, was T at M equals, so Desmos had 18.27 times the sine per k. Desmos had 0.501. I'll just call it 0.5. Phase shift was 4.11. And the axis was 4.05. Yeah, so our hand by hand techniques, did pretty well. Lastly, explain why a sinusoidal function is an appropriate model for this data. Well, there's a lot of reasons to explain this one, but essentially, like we all know, seasonal temperatures basically periodic. It gets cold in the winter, it gets warm in the summer. Usually, the same months are usually the hottest months and the coldest months. So let's just describe it this way. Seasonal temperatures are periodic, usually varying between a maximum and a minimum. So a periodic function is a good choice of model. All right. The last thing we're going to look at is often in nature, you have things like populations where you have, for example, I'll just use a population of rabbits, let's say. Population of rabbits moves into a new area, is eating all the grass, population explodes and grows and grows and grows, but then they kind of run out of grass. They start to die off a little bit, and then they decrease and decrease. But once they decrease a whole lot, there's a lot of more grass now for the ones that are left, and the population goes up and up and up again. And populations dip and increase, and et cetera, et cetera. Also, a lot of these periodic increases and decreases in population for one animal or plant will actually coincide with a rise or decrease in another animal or plant. So we're going to look at that here. We're going to examine a predator-prey relationship. So we have an equation modeling a population of wolves. in an equation modeling a population of deer. And all we're going to do for this example here is we're just going to plot these guys in Desmos and see how they look. And then kind of just talk about why what we see makes a lot of sense. So let's just head to Desmos. We are kind of finished with this guy. So we'll pop in our two equations. I'm just going to turn them into y equals equations. So y equals 500 plus 100 sine x. 500 plus 100 sine x. Our other guy, 2000 plus 500 cosine x plus, man, my memory sucks today, 500 times cosine x. Okay. Now, of course, we can't see what's happening there, so let's change our window settings. So we're going to use our x-axis is going to be years, and for 20 years. So we'll change, put myself back down here. So we'll make our x-axis go from something like -2 to 25. I'll make a step of 1. That should be good. Now for our y-axis, so we've got an axis for the first one, an axis of 500, and we're going 100 above that and 100 below that. And then 2000, we're going 500 above that and 500 below that. So I'm going to do, for my x-axis, from -200 up to 2600 should be good. And then I'll just make the step 100 for my axis. Okay. All right. So those things are looking pretty good. And we can see there's kind of a connection, right? So just maybe pause the video here and have a little bit of thick of that. So look at, so the population of wolves is down here in blue, and the population of the deer is up there in red. So think about what's happening as the wolf population is increasing versus when the wolf population is decreasing, and what's happening to the deer population. And just unpause when you're ready. We'll have a quick talk about that. All right, I'll assume you've had a quick look, but after sketching these guys out, you can kind of see, look what happens as the wolf population is increasing. So as the wolf population is increasing and increasing and increasing up to about, like 1.5 years, the deer population is decreasing. But then the deer population starts to get pretty low. There's not enough food for the wolves, and the wolf population starts to die off. But as they get lower and as the wolf population decreases, the deer population starts to come back and increases. And then there's a lot of deer, food for the wolves, and the wolf population starts to increase. But then they get the more wolves there are, the more deer get killed, and there's this constant interplay between these populations. And this happens all over different ecosystems, so it's really interesting. So just maybe to wrap this up, we'll say this: when the wolf population is increasing, deer population stops growing and then decreases. And then vice versa, when the wolf population is decreasing, deer population stops declining and then increases. All right, so pretty neat. So what do I expect you guys after today's lesson? Well, I expect you guys to be able to, if I give you guys a function to calculate an average rate of change, to estimate an instantaneous rate of change, like we did here, and interpret its meaning, I'd expect you guys to be able to perform a regression. So if I gave you some data, some periodic data, I'd expect you guys to be able to do something like we did in our note here and pick off values for A, K, C, and D and create your own equation that models the data. And then I expect you guys to, given two periodic functions that might be related, to graph them and kind of interpret what's going on and how the two kind of interplay. All right, guys, we finished Unit 5. We got 3 more units to go. So as usual, I've got some suggested practice. Now for C1 to C3 in this page, you can have a look at the investigation we did at the start, the sign function. For question 1, I've got another link here to a similar Desmos investigation, but instead of the tangents of the sine function, it's tangents of the cosine function. And then just a few problems based on what we did in our last 2 examples. All right, guys, hope you enjoyed that lesson. That's it from me. Hope you guys are doing well. Take care, and we'll see you soon.